Hi everyone, this is going to be a video walkthrough on problem 3 on CS621B Spring 2021 exam prep worksheet number 5, which covers iterators, iterables, and a bit of DMS and comparators, which this last question is about. Okay, so quick preface, this problem is particularly difficult, especially if you go for the challenge solution, which is what I'll be covering in this video. So I expect you guys to have a basic understanding of dynamic method selection and comparators, but it's not required because I'll dive into it with a bit of depth as well. So let's go over the problem and then I'll give you guys a bit of time to think about, I don't know, how to approach it yourself, okay? So what we need to do here is implement the comparator DMS comparator, which compares animal instances, okay? And we're going to say that one animal instance is greater than another animal instance if its dynamic type is more specific. What that means is if we have these examples below, right, we can see that this animal object with dynamic type animal, right, and if we look at this poodle object with a dynamic type poodle, we see that poodle has a dynamic type that's more specific than animal, right? And a poodle also has a dynamic type that's more specific than dog. So when we compare a poodle to a dog, we expect a positive number, right? Because how the compare method works for comparators is if this object is bigger than the second object, we expect a positive number. If this object is smaller than the second object, we expect a negative number. If the objects are the same, we expect 0, right? And we can kind of see here that the compare method is scaffolded exactly in these three cases, where we expect a positive number if the first one is greater than the second, a negative number if the first one is less than the second, and 0 if they're equal, right? Okay, so that's just like a basic understanding of what the question is asking and what it means for one animal to be greater than another animal. Okay, and if you guys are confused on how a poodle is greater than an animal, we can see here that a poodle extends dog, which extends animal. So we can see that poodle, if we're thinking about this inheritance tree, is like farther down on that inheritance tree than animal and dog. Okay, so how can we actually solve this problem? If you guys recall from lecture, there's ways of accessing the dynamic type of a given object. But for this question, we're going to restrict ourselves, very important here, restrict ourselves to using the integer variables predefined, which are first, second, fourth, and third. I don't know why I went in that order. And then we can only use relational or equality operators, which include equals equals, greater than, etc., Boolean operators, and or, and parentheses, okay? And then for the challenge solution, which I definitely recommend doing because it's a better test of your guys' understanding, is that we're not going to use greater than or less than or greater than or equal to or less than or equal to. Instead, we will only use these two, okay? It's just like a better test of your guys' understanding. So I recommend doing the challenge iteration of this question. Okay, so just to recap, what all of this is saying is that in these blanks right here, we can only use these variables. We can use like and ors and ands. We can use equals, and we can also use parentheses. Okay, that's all that we have at our toolkit. Okay, so in order to approach this question, I think the first thing to understand is what should be in these blanks right here. Okay, so in this blank, it should be some sort of condition, right, that checks if two animals are equal, right? That's what this first condition should be. The second condition should be if O1 is greater than O2, okay? So that's some like intuition for what these two blanks are, but we actually skipped one thing, is like what should go in this blank over here, okay? So this is just understanding of comparators, less of DMS, is that in order for somebody to be a comparator, they need to implement the comparator interface. And we said in the beginning that DMS wants to be a comparator So it needs to implement the comparator interface, okay? So we will put in implements comparator. And what is this comparator comparing? It's comparing animals. So we should specify here that it's a comparator over animals. And if you guys are like ever confused in the future of what to put here, it should be what the compare method wants to take in. Okay, so with all of this in mind, let's try understanding all the possibilities for these two cases. Okay, I think this is a good starting point, is what are all the possibilities for these two cases? And to help us approach that, let's look at the possible dynamic types of O1 and the possible dynamic types of O2 in this little chart I have over here. Okay, so this corresponds to dynamic types. Okay, so looking at this little chart I made, if O1 is equal to O2, there's one of three cases. Either they're both dynamic type animal, they're both dynamic type dog, or they're both dynamic type poodle. Okay, and we can think about these as these yellow cases that correspond to the first condition, right? So our first condition should make sure that it accounts for all three of these cases. Okay, in order for O1 to be greater than O2, we can see it's going to be one of these three cases, right? Either O1 is a dog, O2 is an animal, O1 is a poodle, O2 is an animal, or O1 is a poodle and O2 is a dog, right? And we can just kind of correspond these to the orange cases. And I think it's really important to draw this diagram so we understand exactly what these conditions here must account for, right? Okay, so with all of this in mind, I think the next step here is to understand how we can use first, second, third, and fourth to help us create these conditions, okay? In order to help us do this, I created a little chart at this bottom. Okay, so what this chart is let's try to figure out the result of calling speak with an invoking instance. What does it mean to be an invoking instance? In this case, it's either going to be, my apologies, O1 or O2, right? It's the instance that invokes the speak method. And we're considering parameters of animal and dog, right? Because those are the parameters passed in to the speak method. Okay, so over here, we can kind of see this diagram isn't drawn correctly, but if we look at this first column, it'll correspond to potential values of first and second, right? And then this column will correspond to values of third and fourth, okay? So if you guys are like a little confused about what this chart is asking, I'll walk through one example and I think it'll make sense. Suppose that O1 is of dynamic type animal. Okay, and then we call O1.speak on some animal object. Okay, that corresponds to this situation right here, where the invoking instance is of dynamic type animal, and we're calling it on a parameter of static type animal, right? Because we only care about the static types of parameters passed in. And in this case, all of the invoking instances, O1 and O2, all have the same static type of animal. So the only way of differentiating them is by looking at their dynamic type. Okay, so looking at this first possibility right here, if we do O1.speak animal and O1 is an animal, what's going to happen during compile time is that we will look in the animal class for a speak method that takes in an animal. Accordingly, we will lock in on this method signature. During runtime, we notice that O1 has dynamic type animal, so there's no dynamic method selection, and what will happen is that we will output 2. Okay, so let's just quickly walk through all of these 6 cases because this will be very, very helpful in figuring out those conditions above. Okay, so the next case is suppose that the parameter passed in now has static type dog. What will happen is that we will simply execute this method up here. Okay, and the reason for that is that we're doing the same exact thing, it's just now we'd rather use this method than the animal method we chose. Right? And then the dynamic type is still animal for the invoking instance, so there's no dynamic method selection. Okay, I'm going to go a bit faster through these next cases, and if you guys are a bit shaky on dynamic method selection, I recommend watching last week's video. So if the invoking instance has a dynamic type dog, what should happen when we do o1.speak to a dog, where o1 is actually, let's think about this case, my bad. Let's say that we do o1.speak to an animal, is that during compile time, we will lock in on this method signature. And then during runtime, what we will do is we will choose this method signature from the dog class, because o1 is actually a dog. Okay, so this one will be 3. And I think it's actually easier just to deal with this next case. So let's quickly deal with that. Okay, so suppose that o1 is a poodle, and then you do speak to animal. During compile time, since its static type is animal for o1, we will still lock in on this method signature. Then during runtime, what we do is we look in the poodle class for the speak animal method, but it doesn't exist. So what we do is, since poodle extends dog, we can still use the speak animal method in the dog class, okay? Because what we do in dynamic method selection is we go to the dynamic type class, and then we keep iterating upwards until we find a method signature that matches the one that we're looking for, or we get back to our static types class, right? So in this case, this will also be 3. So now let's consider the possibility that we're calling our method on a dog, and then we are going to let's consider our dynamic type of dog as well. So in this case, what will happen during compile time is we will lock in on this method signature because we're speaking to a dog, and we look in the animal class. Then during runtime, we try looking in the dog class for that same method signature. None exists, so we settle on what we locked in on during compile time. And then this goes 1. And then during the last case, where poodle is here, we see that we'll lock in on the same method signature, but then during runtime, we actually choose this one in the poodle class. Okay, so we get this according table. Okay, so finally, let's pull all of these pieces together to help us solve this problem. Okay, so looking at this, let me move this up a bit just so we can use it. Okay, so we're trying to tackle this first blank first. And let's recall the first blank is the condition when the two animals are equal, right? That's this condition right here. So for the first blank, we want to deal with the cases of either animal, animal, dog, dog, or poodle, poodle, right? If we look at this table that we had from before, these are the cases that we want to deal with, the ones highlighted in yellow. Okay, so what we're going to do is ask ourselves if this is an animal, right? If O1 is an animal and O2 is an animal, right? How do we know that, like, how can we use this data to say that they're both animals, right? I think that was a little poorly worded, so I'll say that again. If O1 and O2 are both dynamic type animal, how can we use this data, right, in this little table that we just made to help us assert that they're both indeed animals, right? And the important thing here, which is maybe a bit obvious, but I wanted to drive it home, is that if you're a dynamic type animal, dynamic type dog, dynamic type poodle, this pair that you get out is unique, right? Which means all we need to do is compare this pair. Okay, so what does that mean? Well, we know that first corresponds to this column, right, on O1, right? If we look at second, it corresponds to this column on O2. So what we can say is that if first is equal to second, it means that this column is equal and third is equal to fourth. It means that this column for O1 is equal to the value in this column for O2. In other words, what this check is saying is that if we look at the pair in this table, right, they're going to be the same. So this check right here is indeed checking that the dynamic types of the objects are the same, right? And we could have honestly like stumbled upon this without rigorously walking through all of these measures. But it's very good to like know for sure that this check accounts for all of these possibilities, okay? So let's keep going. In this else if blank, this is a very difficult part of this question. We need to return, or this condition should evaluate to true if O1 is greater than O2, okay? So if O1 is greater than O2, we remember that it's going to be one of these three possibilities, right? Either O1 is a dog and O2 is an animal, O1 is a poodle, and O2 is an animal or a dog, right? Those are the three possibilities, okay? And what's also good to know is that we know that none of these cases exist anymore because they got accounted for in this first if check, right? So we know that if O1 is, this is very cool, if O1 is a poodle, we know that it has to be the biggest, right? Because we know that O2 can't be a poodle because we accounted for this condition right here, right? So what we can say, I think this is our first line of evidence, is if, I'm going to write this in pseudocode, if O1 is a poodle, right? This is saying that O1 is greater than O2 because O2 can't be a poodle because the first check would have accounted for that. So if O1 is a poodle, we know that we want to return 1. The other case, that accounts for these two cases right here. The last case that we need to account for is if O1 is a dog and O2 is an animal. So if O1 is a poodle or O1 is a dog and O2 is an animal. Okay, these are the cases that we want to return 1 for. So let's translate these to code using this table that we made over here. Okay, so this case, that if O1 is a poodle, it translates to us looking at this section of the table, okay? So notice that if O1 is a poodle, only poodles have a 4 for this spot right here, okay? So what we can say is that if O1 is a poodle, translates into us saying that third is equal to 4, because third corresponds to O1 that speak to a dog, which corresponds to this spot in our table. Okay, so to recap, this is saying that O1 is a poodle. Okay, so the next thing that we need to account for is if O1 is a dog and O2 is an animal, okay? In order to account for this case, how do we know for a fact that O1 is a dog, okay? So this is kind of cool. We know that O1 is a dog if this number is 3. The reason for that is we know that O1 isn't a poodle because if it was a poodle, we wouldn't be checking this condition right here, would we? Right? So we know that if we're checking this second condition, it means that O1 isn't a poodle, so it has to be either a dog or an animal. And we know that we differentiate a dog from an animal in that this number is different, right? This number corresponds to the value of first, right? So what we can say is if O1 is a dog corresponds to us saying if first is equal to 3. So let's put that in there, right? So if O1 is a dog is if first is equal to 3, and O2 is an animal corresponds to, well, if O2 is an animal, it means that we're looking at this entry right here. And we know that a fact is that all animals have a 2 in this spot in the table, right? So a way to figure out if something is an animal is if there's a 2 right here, because dogs and poodles have 3s at that spot. And that corresponds to looking at the call to second, right? So what we're going to say here is that if first is equal to 3 and second is equal to 2, it corresponds to the case that O2 is an animal. I already have that written, right? So that is all for this question. I hope you guys understand it. And yeah, I'll see you guys next week.